until 5:30, or it doesn't get dark till 8:30. Well, then put a photocell in series with the time clock, because I don't want the lights to be on all night long. I like the lights to come on at dusk, but because this is a sign and this is parking lot lighting or whatever the case may be, I want to make sure that we turn off all the lights at 11 o'clock. By that time, guess what? There's not enough traffic. We don't worry about people seeing the bank. So you put the time clock supplying the photocell that and if the time clock goes on at 5 and cuts off at 11, but the photocell says, okay, today is 6:42 before it becomes sunset. Well, time clock is closed and the photocell has closed. Now the light energizes the contactor, the circuits become energized. However, at 11 o'clock, even though the photocell showed a contact being closed, at 11 o'clock, time clock says, we're opening, lights turn off. So it's a really convenient little way of doing it. We're now moving to Unit 6, magnetic motor starters. We just kind of got done with the contactors. This unit covers the operation of single-phase as well as three-phase magnetic motor starters. A magnetic motor starter is essentially a magnetic contactor with an overload relay assembly added. And Steve, you talked about that and you showed it earlier. And I'll have you get that device again. There we go. We show auxiliary contact. Here, this is the overload relays right there. So current comes in, goes through the make and break contacts, then it goes through the overloads. And we'll talk more about that. And then looking at Steve,
there's the overload block down here.
the overload block is right down at the bottom down there. Can you see the overloads from that one?
Yeah, right here in the front, this part that,
Oh.
Tip it a little forward.
if I, forward,
There you go.
that help?
Okay. Yeah, I thought
This
there was
very
a better.
front
We
part
had some
that's-
overload somewhere else. I thought we had something. Maybe Dan has an overload. Show us what it might. Okay. Is there anyone better than that?
Actually, that's the heater mechanism of the overload, and then your actual, I don't know if you can see
Snap,
down
don't
in
want to go
here.
there. Just want to see the overloads, what they physically look like. All right, looks like Dennis has an overload in his hand. There's a couple different configurations, and so little devices that current's going to travel through. We'll get some better slides, and we'll show this in a second. So anyways, the fact is this. You got a contactor, and in addition to the contactor in series, before you get to T1, 2, and 3, if it's three-phase, we put a device in series that's going to be sensing current and heat. Now, one of the things that took me a while to understand, I'm afraid I'm going to get ahead of the game, but I have no choice. I'm afraid I'll forget it, is that when the overloads open, the overloads are not opening. Here's the overloads. They're heating up. What is opening is the contacts for the okay, let's take a look at it. Line 2, the overloads are in series with the coil, but these are the heaters. I know this is kind of like getting kind of confusing, and I'm not doing a good job. So, like I said, I'm ahead of the game, but I don't know how to do it. So let me just say that the heaters are the sensing elements. They are not going to actually open, but there's a set of contacts with each of the heaters that we're going to put in series with each other, that's in series with the coil, that if any one opens, then we drop out the coil. Do you have something, Dan, there at all that could maybe help the guys to see?
Where he showed that they put those in, these have different size wire
Yeah?
for different size motors. The finer wire would be for the smaller motors, and they're designed so that at the correct amount of current that goes through these, it will heat up to a certain level. Of course, then we're going to talk about, you have the bimetal switches that work, or you have the solder pods.
But 1 second, if we're heating up something, then if it goes past a certain point, it will then open a contact,
Yes,
right? The
exactly.
heater itself that you just showed me, current is still can go through it. Whether the contact open or not, the current can go through it.
Yes.
So the heater is just simply like the ability to capture the heat, transfer it to something, that something else measures the heat and says, hey, we have a problem, and it opens a contact. And it's, we'll get there. It's just kind of like, I'm not quite sure. That's okay. I can understand that. I'll just go a little further, and then we'll keep building on this. Overload relay motor running protection. Overload protection devices are intended to protect the motors, the control, the branch circuit conductors against overloads that cause excessive heat. Now, there's different definitions in Article 100 that we got to be aware of. There's a definition of overcurrent. Overcurrent includes the condition of overload, short circuit, and ground fault. Now, what is overload? Overload is when you carry more current than something is rated. An example, if you had a 15 amp circuit breaker and you had 15 amp conductors and you happen to have a 20 amp load on a 15 amp circuit, well, the 20 amp load would be an overload condition because it exceeds the load rating of that circuit. Short circuits. Well, what's a short circuit? Well, if you go phase to phase, there's no definition of a short circuit, but you just got to know what it is. That's a short circuit. Phase to neutral would be a short circuit. Then you have a ground fault. A ground fault would be phase to the equipment grounding conductor, which would then have the fault current returning back via the source. So we're not looking to provide at this moment through the starter. Let me go back to the starter. This starter, we're not looking to provide any kind of overcurrent protection. We're only looking to provide overload protection. That's why they're called overloads. Overload protections are intended to protect the motors, the control, the branch circuits against overloads that cause excessive heating. What's an overload? An overload is when you have current exceeding the rating of it, but it's not a short circuit and it's not a ground fault. All right, let's understand what's going on here. When a motor starts, depending upon the code letter of the motor, depending upon the application, the easiest one to work from is the motor will start at 6 times its rated current, and it will start at what is called lock rotor current. We're not going to get into details to explain. This is covered in the theory course. So it starts at 6 times. It's standard number. It might be more, it might be less. It could be a lot more, it could be a lot less. It starts at 6 times for the starting current, then it goes to 300, then 150%, and eventually it runs. So let's just assume that this was a 10 amp motor. If this was a 10 amp motor, running current would be 10 amps, but what would be the starting current? 60 amperes. So we have a unique situation when it comes to motors, because let's take the lighting circuit. If you had 100 amps of lighting, well, when the lights run, you have 100 amps of lighting. When the lights start, forgetting about instantaneous, you have 100 amps of starting. Well, in that case, you could put a 100 amp breaker, let's say if it wasn't continuous, protecting a 100 amp wire, supplying a 100 amp load, because it starts at 100%, let's say, and it runs at 100%. But when you get to motors, if the motor starts at 6 times the running current, well, then you'd have a problem if you put a 100 amp breaker on a 100 amp motor, because when the motor first starts at 6 times its running current and it runs, let's say, at 100 amps, you'd have a 600 amp starting current on a 100 amp, let's say, breaker for a 100 amp motor. It's not going to start. So the problem with, in order to provide the proper protection for motors, you have to size the breaker, or let's say the fuse that protects the circuit for the branch circuit. That's going to have to be sized considering the starting characteristics of the motor. And those percentages could be a lot of different options. But let me just distill it real simple. 43052 in the National Electric Code talks about, C1 talks about that there's a table that we use. And for circuit breakers, just for general application, you would size the breaker at 250% of the rating of the motor current as listed in the code book table, 430, 240, 248, 249, and 250, depending upon the application. So you get the motor currents on the code, FLC, you go 250%. That's to allow that breaker or fuse, that breaker to be sized sufficiently large enough to allow 600 amps or 600% starting current. That is going to be protecting that motor, though, and the apparatuses and the circuit conductors in the event of a short circuit. Short circuits are going to be many, many more times rating than the rating of the actual motor running. So 250% protection for the motor circuit should protect the motor against shorts and ground faults. So let's go just a little further. Let's take a look at this example. Here is a 16 amp motor. We size the breaker at 250%, and if it's 250% of 16, I think that comes out to be 40 amps, or fuse, let's say. Well, this happens, fuse is between 150 and 300%. Circuit breakers are going to be 250%. I mean, depending upon whether it's a fuse or circuit breaker. Let's go with this here, circuit breaker. If we had a circuit breaker on a 16 amp motor load, that would be a 40 amp circuit breaker. And that 40 amp breaker is intended to protect this motor only against short circuits and ground faults. Here's a short circuit, draws 1200 amperes. That breaker is intended to open the circuit, short circuits and ground faults. Over here is the overloads. We call them the heaters. Again here, overloads and heaters. The problem is that the overloads and heaters are very slow responding. If you have a short circuit of 1200 amperes, these overloads and heaters are not intended to open under short circuit ground fault conditions. That's the purpose of the circuit protection device. However, if you put 24 amps of a motor that's supposed to draw 16 amps, and you happen to have a 40 amp breaker, well then that breaker is not going to sense the overload. So what we have to do for motors, we have to have overload protection, which is the overloads of the heaters. Then we need to have short circuit and ground fault protection. Now, we're not into motor circuits, and I'm almost sorry that I even got into this discussion. But I need you to understand those heaters are going to be sized a specific manner in the industry as well as a code. And they're there to provide overload protection, not short circuit protection. And I know this is code, and if you don't know code, we'll see if we can put a few sections in the back of this book talking about some basic NEC requirements, and that might be something that you can review. How do you size the wire to a motor, single branch circuit? How do you size the protection to a motor? Maybe some requirements, NEC requirements having to do with motor control circuits, maybe motor controllers. So we'll see if we can put something in the back of the book, a little annex in there about NEC requirements based upon the 2008. As time goes by, it's going to change. Let's go back. Overload motor protection is to protect the motors, apparatuses, and branch circuit conductors against overloads. Okay? Overcurrent protects against overload, short circuit, and ground fault. We are not protecting against overcurrent for motors, for heaters. We're protecting against overload. What's an overload? Current in excess of the rating of that particular application. Motors, what happens with motors? They start at 6 times the lock rotor current, the running current, and then they go to 100%. Because of the starting characteristic being different than running characteristics, overloads will protect the motor under running conditions. Short circuit and ground fault protection device protected under starting conditions or short circuits and ground faults. If you have an overload of motor draws 16, you draw 24, your short circuit protection devices will not sense it, but the overloads will. If you have a short circuit, the overloads are not intended to protect against short circuit and ground faults. That's the purpose of the short circuit ground fault protection device. The combination of the branch circuit, short circuit ground fault, and the overloads will protect that motor against overcurrent. But they're different components, and they are sized differently. Now, the National Electrical Code says how you can size the overload protection devices. Then they get into temperature rise and service factor, and you got to go to the motor nameplate, and there's code rules that tell you how to handle all that. But we're going to put that all aside because in reality, you're going to be sizing the overloads by simply looking at the motor nameplate. Let's take a look at this graphic here. We're not going to get involved in the service factor and the temperature rise and all the other stuff. We're going to look at the motor nameplate, find out this motor has a nameplate current rating of 28 amps. Based upon the motor nameplate rating, we simply go to a table that's given by the manufacturers that's provided for that given starter. And Dan, you had that little tiny device. Any of those have a number on them? Any kind of B number, anything, have something identified in some way? What does that one say?
The GE ones are actually pretty good because the part number is actually the amperage. C955A means that this one's good for 9.55 amps.
Oh, that's a GE.
Yes.
So, okay, and Dennis, what do you have?
This is square D, B 19.5.
B 19.5. Now, I don't know what that means. We'd have to go into a table like this right
Well,
here.
It's rated 19.5 amps.
Oh, is that right?
Yeah.
I did not realize that the numbers on the overloads.
A lot of them are, some of them aren't. This one, for instance, is a Allen Bradley, another American company. W77. This one is off probably a 125 horse motor. So you can see the amount of metal that we're heating up is quite a bit more in this one. So
Help me here, because I'm looking at this table that we have here on the graphic. It says 1 TU, 2 TU, 3 TU. What is that? Why are they different? Do anybody have an idea what that means on that table?
Well, for the Allen Bradley bulletin that's like this, that would refer to the size of the starter. I'm not sure if that's what it is in this particular instance, but the first column would be for a size 1 starter. At this nameplate, you use this thermal unit number. For
Okay.
a size 2 starter.
Okay, I need practical here. And Dan, you're the one that's actually right now working in the practical application. How do you size the overload protection device that you put? Are you using electronic and you're not even using these at all?
no, we use these. These are some of the ones from our mill. We start out at 100% of full load current.
All right, hold on. So I got a motor and it draws 10 amps. Then you go and you find an overload device that's rated how many amps?
10 amps.
10 amps. And you put that baby in there.
And then if it holds, we're all good. And that's because we're more on the maintenance side of it. We can go up to the maximums that are in the code, but we like to start out at 100%. That way you're protecting the motor even better.
Okay, so if we go back to the slide here, the code tells us, listen, you know, you could set the protection device at 125% of the nameplate. If you
Yes.
want to. So in your case, if you had a 10, or in our example, if it was a 10 amp motor, and if it had a service factor 1.15 and up, and we go to this label and it says 1.16, well, it's 1.15 and up. Well, 1.15 and up and 1.16 is in that condition. Well, then I would set it at 125%. Well, I could set it at 125. But you're saying,
Yes.
you know what? We'd like to protect this motor. So we'll set it at 100%. And if it doesn't work, then we'll adjust it up. But we probably won't exceed the 125 because now you're allowing possible excessive heat. And you might not burn the motor out initially with excessive heat, but just a small percentage rise in heat reduces the life cycle of that motor substantially. So what do you do if what do you just go to next size up if it
Normally we'll take amp readings and see what it really is running at. And if we need to go upsize them, then we'll size them up.
is it possible the motor is just overloaded when you take the amp reading? In other words, it was supposed to draw 10 amps and it's drawing 12?
Well, yeah, if it's a,
In other words, the motor might not have been properly sized for the application.
that's correct.
And so that's another way by taking the amp reading and finding, hey, listen, we have a bigger problem than just overloads here. We got a motor that's being stressed, that's being used an excessive amount of current, that's going to be overheating and ultimately going to be failing.
Then we'd want to look at upsizing the size of the motor to be correct.
Dan, Dennis, any feedback? Anything else?
I agree.
All right, so we get the nameplate rating. We size it 100%. Maybe this is, and then of course you can kind of go to the table. The manufacturer will have the tables inside the contactor telling you what size and maybe what kind of thermal number that would actually be used for that given application.
Mike, I think what they're showing there on the top, the 1 TU, 2 TU, and 3 TU is the number of thermal units. So that left column would be a 120 volt application, and the second one is a 2-pole starter, a 240 or a 208, just using 2 lines, and the third one is your 3-phase.
Okay. And so you'd still use this B039 for these combinations. So that's allowing to go, 1, 2, and 3 pole. All right. Overloads include, well, when would you have a case of excessive amount of current? Well, there's low voltage to the motor. Anytime you reduce voltage to an inductive reactive motor load like that, you're going to create increased current. Eric?
If you've got a motor that's hooked up to a fan and the pitch of the fan is too high, you'll overload your motor.
Then it's being stressed.
Right.
lock rotor current. I mean, the motor locked, something jammed. Someone was supposed to go through, and all of a sudden it jammed. And now the motor is struggling to turn, and it's locked rotor, and it's drawn back at the 6 times. Motor's just too small. Unless you're a fan, I mean, it's too small, or whatever the case may be. Bad bearings. I think I heard somebody talking about, I don't know why I just hear this recently, about bearings to some large motor that the bearings just kind of wiped out. Well, if the bearings go down, obviously it creates a lot more drag and friction, and motor starts carrying excessive amount of current. Single phasing, where you have a 3-phase motor and then one phase drops out. I can't remember, what is it, 59% rise in current on one phase, or whenever you single phase a motor, I forgot exactly what happens to the current and percentage of the current. But either way, if you have a 3-phase motor and you single phase the motor, meaning you drop out one phase while the motor is running, that motor could continue to run, but an excessive amount of current, that's overload. It's not short circuit and ground fault. So we want to make sure that we provide protection against that. Let's talk about different types of ways of providing overload protection, and remind me, I think I remember this. All right, what can we use for the overload device? How do you say this, Eric? What's this?
Eutectic.
Eutectic alloy. What's eutectic mean?
It's a metallurgical word that means that a combination, an alloy of metals melts at it's like a minimum point temperature.
So it's like they can tell what that's going to melt at.
Yeah, the eutectic alloy is a mixture of metals that the percentages of the mixture is such that that percentage causes it to melt at the lowest point of that percentage of those mixtures. Solder, in other words.
I haven't been able to yet describe this, but here is a symbol for the overload. When current travels through this device here, it creates heat. This heat has this ratchet wheel already turned, and here's a ratchet wheel right here, and this pawl is going to a set of contacts. And the way it's set right now, the way this ratchet is turned, and maybe, Dennis, you might have one there. Let's see if we can zoom in on yours right there. There's a pawl right there. And if you try to turn it, Dennis, you can't turn it. Is that right?
Solid.
It's
very
solid.
solid.
But if it got hot enough and it's eutectic alloyed, it would melt, and then all of a sudden, it would release.
And because internally in your contactor in here, this is a spring-loaded mechanism. So, I mean, if we could actually physically look in here, you could see a ratchet or an arm that holds back on this wheel.
Now, behind each of those, well, those heaters are going to go, there is a set of contacts, little contacts. And so we have the heaters that are heating that eutectic metal, and when you press that reset button, you're loading up the ratchet, and you're loading up the contacts, and you're closing all 3 of those contacts internally.
Well, typically there's usually only one contact, which is off to this side right here.
Okay, there's one that would,
Right.
okay, the ratchet, okay, any one of the 3, though, would heat up, would release that contact that's being held closed.
Correct.
So you press the reset button, it loads it up, it closes the one contact for the overload, and any one of those 3, if they melt because of heat, would open that contact. And let me go ahead and find that picture right there. Any one of these 3 could melt that eutectic metal, releasing the latch, causing this contact that was being held closed to open. Are we there, guys? Is that okay? Am I saying it right?
Exactly.
Okay. So now let's go take a look at it right here. So when you press that reset button, it pushes this down. Right here. Here's my control circuit right here. This is the control circuit. It pushes this down, so now my overload is closed, and it's being held closed. But here is the line conductors. Line coming in, line 1, and let's say T1 going out. Current travels through here, travels through the heater. It heats this up, travels to the load, and if it heats it up to a certain temperature, it then will melt the eutectic alloy inside here, releasing this ratchet, as shown right here. It just turns it, and all of a sudden, the control circuit contacts open. The heater is only allowing that contact to open, but the heater still would have continuity even though the control circuit contacts open. Let's take a look at this one here. So, we press a button, we load it, we close the control circuit, the contacts and overloads are closed. There's an overload condition, it melts the alloy, it then releases because there's a spring action there, it releases it, now opens the overloads, and of course the overloads being used in a circuit would then stop the circuit if that was the purpose of that. What do? Well, you have to make sure the alloy cools sufficiently. Once it cools sufficiently, then you can press the reset button and then reset the overloads. So it really is two parts. You have the contacts that are normally open that'll be set closed, and it's the heater that would be releasing the energy that's holding that closed. It's important to remember that there are two parts of the overload. I just described that. The actual overload device and the closed overload relay contacts. Here's the overload device, and behind that is the contact, and that allows us to reset that contact. Any comments? Extreme care should be taken if the contactor has been de-energized because of an overload.
There, Mike, it's because something happened to that motor to call for more ampacity to keep the motor running. Either the bearings went bad, you know, it got hit by a forklift, something's wrong with that motor, and I've actually seen demonstrations where contactors explode because they get reset without somebody going out and physically looking at the motor.
So anytime the motor drops out, the starter comes out, there's a problem. I mean, it's like a GFCI. If a GFCI trips, there had to be a reason that the GFCI tripped.
Right.
If the circuit breaker tripped or the fuse blew, it isn't like, well, let me just press the reset button and we're fine. Or let me just go ahead and close and disconnect again. Or let me go ahead and replace the fuses. We got to find out, well, and what you said, Dan, was, well, we put an amp meter on there. What happened?
Okay.
I mean, something had to happen. Why is this thing drawn? Why did this thing burn out? So, and you don't want to be going in there and resetting that without knowing what was the condition. Overload relay symbols and schematics. Now, I'm confused about this particular graphic right here because we show 3 overload relays, and then we show all of them together. So you guys got to help me because you're the experts. Is there one only, or is there 3 in series with each other that any one of the 3 could open in physical, practical sense?
Yes.
Depends on the manufacturer.
Okay. Okay.
And the older style ones did have 3, and they had 3 reset buttons.
Oh,
Three
Steve,
there.
here, look at Steve's. Steve,
there's-
show us the
there
3
it
reset
is.
buttons.
Well, you can see that there's 3 heaters right here.
What are the 3 reset buttons on it?
Well, each one of them has their own set of overload. Well, no, there's not 3. This one must be on an automatic reset.
So, okay, what is the practice today? Is it a single overload?
Almost all the new ones have one overload switch that's by any 3. The older Allen Bradley did have, and in the 60s,
Yeah,
they only
like
had
this.
2. And then I forget
That's
what
right,
code
because of
change it
code.
was, then they had to have 3. And the
All right.
ones that had 2 did have individual switches.
All right, so really, whether it shows it one for each one, or whether it just shows all the overloads individually, basically it comes down to this. Whether it's 1 or 3, you come off of line 2, you're going through the overload contacts that are being held closed mechanically, that goes to one side of the coil, and if you provide power to the other side of the coil, then you energize the M coil, which closes the main contacts motor runs. If any one of the 3, or if there's just one, however it works out, opens, it de-energizes the coil, opens up the normally open M contacts that were being held closed.
Right.
Here's another example how it's shown. I like ladder diagrams. I mean, looking at that right there, to me, is just a lot more work than, okay. A stop button's in series with the start button. We haven't gotten to auxiliary contacts yet. And then here's the overload. So if I press the start button, energize the M coil, as long as the overloads are all closed, well, then I can energize the M coil and it's going to do whatever the M coil does.
Other than the manual starter that we showed and talked about earlier, the overload's going to be the only thing that you put on the load or the line 2 side of the coil.
Okay. Other than a manual starter, on the line 2 side is going to be the overloads, but that's already built in the contactor,
Yes.
right? I mean, the line 2, do we have that as shown? The line 2 is connected, and the overloads are already rewired. So let me go back to this picture here. This line 2 connection through the overloads to this side of the coil, that's taken care of. Okay, you got that on your Dennis there?
Yeah. That's what we were talking about earlier.
Yeah, that's already pre-wired, so we don't have to worry about that side of the coil. So if the overload's open, that's all done internally of that starter. If it opens up, we just got to make sure that we get the control wiring. We're working on line 1 side is to get the controls, to get that coil energized or de-energized, and whatever the application is going to be. I like that. Good point. Troubleshooting an overload condition. In a new installation, repeated overload trips may indicate the next size up overload is necessary. And we already talked about this and the different things about troubleshooting and finding out what's the problem. Here's a little larger selection. It's in the textbook there of devices and the numbers and how it all works out. And you're going to get this from is that on the inside cover of the starter that has this number in there?
On the MCC door,
Yeah.
typically, yeah.
So you open it up and then the information is going to be right there. We're now in Unit 7, Basic Control Circuits. This will be the end of this particular DVD. We'll finish up Unit 7. The basis for most control wiring is either a 2-wire control circuit or a 3-wire control circuit. The 2-wire control circuits are used for self-starting applications such as pumping stations, air conditioning equipment, refrigeration equipment, etc. All right, let's take a look at a 2-wire control circuit. We discussed earlier that line 2 through the overloads to one side of the coil is automatically taken care of by the contactor manufacturer. Is that a statement that I can make that is a true statement, guys? Dan?
Yes. Yes.
Everybody? So that takes care of that. So we're not going to worry about, and we'll make sure that we won't color that side of the coil. We'll keep it black because we're not going to be messing with it. So now we're going to come off of line 1. If somehow I could get power from line 1 to the other side of the coil, I'll energize the M coil, and by energizing the M coil, it will then draw in and close all the M contacts. Now, they're not identified, but this is an auxiliary contact that will be held closed, that will be brought in closed. M1, 2, 3 contact will be closed. If I can somehow get voltage to the other side of the M coil, because we have voltage now to this side. So I go to line 1. I come over to some device. It could be a pressure switch, a mechanical switch, all the different types of pilot devices that you taught me, Dan. They're pilot devices. Whatever it takes that causes this to close, if I can then take line 1 over to a 2-wires circuit, which is just a toggle switch. I mean, just a switch. If I can close this contact, that then would get me power over to the M coil, and the result is that energizes, closes the main contacts, motor will run. All right? And by the way, as this is shown, and we probably should make this maybe black, is that this is already pre-wired. So all we have to do is come off of line 1 and then go over to this one terminal here, and the auxiliary contact would be, is it always marked as number 3 on the contactor?
Normally it's marked as number 3, yes.
Okay, so normally, so then we just come off of line 1, go to your 2-wire device, and then come off of that device and go right back over to this particular terminal. And my guys, take a look at the contacts now. All right, let's take a little bit more. A 2-wire control circuit shouldn't be used where automatic restarting after power loss will create a safety hazard for personnel working around the restarting equipment. Let's look back on this again. All right. If this was closed because the water level or the flow or whatever the case may be, then this would be energized, the contacts would be closed, the motor would be running, and if we lost power, then the motor would stop. But the moment power came back on, since this was being closed already, this will automatically restart every single time you have power. Let me give you some examples where it'd probably be a good idea. You have an air handler. You got air conditioning. Well, if you lose power, well then, obviously, no power in the building. But when you have power come back on again, well then your blowers, your air handlers, your equipment will automatically come back on again. And that would be a practical application. I didn't work in a hospital, but I've done work in hospitals. When I was a contractor, I did a lot of energy management control where you would go into the control circuit and add another device in series with the control circuit, which you talked about, and by putting another device in series, and the rule was,